Welcome all to the second lecture of this series on an introduction to switching adaptive control by Professor Daniel Liberzon. If we have any questions for Professor Liberzon based on yesterday's lecture, we'll take a couple of minutes to ask those. Is that fine, Dan?
Yeah, sure.
Okay. So, anybody has any questions? Okay, so then we'll move the question answer session towards the end. So you can start, Leonard.
Okay, so thank you for coming to my second lecture. So what I will do today is basically finish the discussion that we had and then open it up for questions about either of the two lectures, or hopefully if you have some other types of problems that you guys are interested in that might be tackled by the same methods, we can try to talk about other things as well. This is where we left off last time. So actually, I think today I will only need about 30 minutes to go through the rest of the slides, and then we can open up the discussion. So I presented to you yesterday. Let me actually flip through here just to remind you a little bit about what we were doing. So we were discussing this supervisory control approach where you're switching between a family of controllers, and the switching is orchestrated by this high-level unit here called the supervisor. And the setting was that the plant had large-scale modeling uncertainty, and this is why we have a family of controllers, each tuned to some specific range of parameters or sub-range of parameters, and then the online estimation type algorithm decides which controller to switch in the loop. And we discussed how the supervisor consists of 3 blocks shown here: the multi-estimator, the monitoring signals generator, which is basically just a filter, and a switching logic. And then towards the end of the yesterday's lecture, we reached this point where we identified the basic properties that the individual blocks should provide. So the first one I'm not going to discuss in detail, but it basically is something that observer-type multi-estimators typically give us, and there is for the linear case, for linear plans, there are general results available from the adaptive control literature, which basically say that the property says that the matched estimation error should be small in some sense, and small means convergence. In the ideal case of no disturbances in model dynamics, and bounded, so gracefully degrading in the presence of noise and disturbances. We also have on this first property some results for special classes of nonlinear plans. And so those of you who want some more details, just contact me and I'll be happy to provide them. There are also references in the last chapter of my book on switch systems that address this point. The second property, before we get to the switching logic later on today, the second property is the candidate controllers should provide detectability. Each controller should provide the closed-loop system detectability with respect to the corresponding output EQ, which is the estimation error EQ. And we recalled last time that the detectability means small output implies small state. Standard notion for linear systems also has counterparts in nonlinear system theory. So let me discuss a bit about this. And so now we are in the third point in the lecture, which is where we touch on how to achieve this design objective. So the candidate controllers, let me focus on this situation here where I have a fixed controller, P sub Q, so it's not switching yet, it's a fixed index Q. And this controller is connected in feedback with the plan here, and there's also the multi-estimator, and this is needed to generate the corresponding estimation error, E sub Q. And I want us to think about this diagram in a specific way, which is the following. So what I did here is, starting with this diagram, so first ignore the text below. Actually, for some reason, it should be animated, but it's not. So ignore the text below for right now, and just focus on this diagram. What I have here is I enclose inside the box the interconnection of the controller with the multi-estimator. And if I do this, so this diagram is actually equivalent. If you get a copy of the slides later and compare this slide with the previous one, the diagram is equivalent. It's the same system. And now the estimation error is coming in as the input to the system inside the box. Okay, so it's a relatively standard way of thinking, standard trick to separate the plan from the controller design. So you think of the controller connected to the multi-estimator. These two blocks are things that are part of our design, and then the plant is somehow separate from these two blocks here. And the basic lemma, if you will, that's valid for the linear case, but also has nonlinear counterparts that I'll mention in a minute, is that this type of feedback interconnection is detectable with respect to the signal here, this output shown by the red arrow, if two properties hold. One is that the system inside the box is stable, and second, the plant is detectable. So in other words, and this is kind of an important observation that's the starting point for more advanced results along these lines, is that rather than working with the property that the controller should provide something for the overall closed-loop system, which is hard to characterize because the plant is uncertain, we're breaking it up into two pieces, two properties. One is that the controller should stabilize the multi-estimator, which is a more reasonable thing to study because the multi-estimator is known, the system that we designed. And the second property is that the plant should be detectable. And here, by detectable, I mean the following. So the plant has both the input and the output. And by detectability of such a plant, I mean that if the external signals are small, so if both the input and the output are small, then the state of the system, of the plant, should also be small. Okay? And I'm stating this here informally, so the proof that I show here is also informal, but you can make it rigorous. But for building intuition, it's useful to go through this simple signal chasing argument. So we need to show that the overall interconnection is detectable, which means that if E sub q is small, let's say converging to 0, then the states of all the blocks here converge to 0. And the way you do this, you assume that EQ converges to 0, and then because the system inside the box is stable and it's linear, so it has the property, the input to the system, which is EQ, converges to 0, then the internal states of the system inside the box, which are the controller state, X sub C, and the multi-estimator state, X sub E, go to 0. So this follows from property 1. Then, of course, the signals U and Y sub Q, which are generated by the controller and the multi-estimator, respectively, also go to 0. So these are linear outputs of these states. And then if you now recall that the output of the plant is given by the combination, actually the difference of YQ and E sub Q, then you see that that goes to 0 as well. And now we've shown that the external signals to the plant are small, and now invoking the second property that the plant is detectable, we see that the state of the plant goes to 0 as well. Okay? This is kind of a toy case, but this is the way that the analysis usually goes. One tries to break up the system into isolating the plant, and on the other hand, working with the interconnection of blocks that are part of the control design. And by imposing appropriate assumptions and verifying these assumptions for the individual blocks, one can then argue about the overall interconnected system.
So Dan, there is a question here.
Should the states be going to 0 or maybe going towards some constants or some reference trajectory? Are these XPs only the variations around reference trajectory?
Yeah, so here I am taking just convergence to zero as the property that I want to have. If you are interested in tracking a trajectory, and that actually people have looked at in the context of supervisory control, essentially the analysis would proceed in the same way. You would just focus on the error dynamics, the error between the output of the plant and the trajectory it's trying to track, and you would adapt this thinking to that scenario. So maybe some small changes would be necessary to kind of relabel everything, but you would show convergence to zero, the tracking error, in the same way as I'm showing here, convergence to zero of the plant state.
Yeah, now I can hear. So, can you full screen your presentation as well?
I'm sorry?
Can you make your presentation in a full screen, put it in a full screen mode? It's
Full screen.
Yep, that's good. Thanks.
Okay, sorry about that. Yeah. Okay, so this was the basic way that the analysis goes for this interconnection, and like I said, there are also nonlinear versions of this result. I'll just spend a couple of minutes. So I don't assume that most of you are familiar with the notions of input to state stability, or ISS, and its dual notion of output to state stability, or OSS. But these are notions developed in the late 1980s by Eduardo Sontag, and they're now widely used in nonlinear system theory. And they basically generalize the notions of both linear stability and also induced gain of the system. So you say that the system, a nonlinear system, is input to state stable, or ISS, with respect to some external signal, V, if its response is upper bounded by a combination of two functions like this. The first one is decaying with time and increasing with the size of the initial condition. This is a so-called class KL function, if some of you might be familiar with that. And this is a nonlinear gain function of the supremum norm of the external signal on the interval between 0 and 2. So once we take nonlinear stability notions of this kind as representing stability in the presence of external signals, then, and we have papers where we wrote down these results. There are nonlinear versions of this idea that can be rather easily obtained. And there are also variations where instead of supremum norms, you use integral norms. So here, compared to the previous slide, where I had some nonlinear gain function of the supremum norm of the input, now I have integral of some nonlinear gain function of the norm of the input. And this is useful in supervisory control specifically because, as I discussed yesterday, we integrate the errors to obtain the monitoring signals represented by integrals of some functions of the errors. And so this integral ISS formulation turns out to be quite compatible with that. So like I said, I'm not going to go into technical detail on this, but I can point you to the literature where these nonlinear detectability results are developed in the ISS framework. There are also relaxations where, and this is quite a standard assumption in adaptive control, where you strengthen detectability of the plant to a minimum phase property. So in the linear world, that would be that the zeros, or transmission zeros of the plant, are in the left half plane. There are also nonlinear versions of the minimum phase property that we have been working on. And under this assumption, it actually is enough to ask that the system inside the box, inside the yellow box, is only output stabilized. So rather than asking that it's stable, you ask that its output given by the YQ signal here and the U signal here are stabilized. So you trade off, you strengthen the assumption on the plant, and you relax the assumption on the system inside the box. And if you get the two assumptions right, again, the analysis proceeds in a similar way as before. So again, the overall idea here is that you use some standard results on stability or on showing stability of interconnections of several systems by borrowing some tools from nonlinear system theory, small gain theorems about cascade connections. So there are quite a few tools that nonlinear system theory has developed that can be used for this purpose. And in case the dynamics are linear, these reduce to fairly standard results in linear system theory. Okay, so let me know if at this point there are more questions about candidate controllers, because what I'm going to do next is look at the switching logic. Let me remind you where we were with the basic properties, basic design objectives. We wanted the switching logic to provide two things. We wanted the estimation error E sub sigma to be small in terms of the smallest of the individual estimation errors, and we also wanted the detectability property to be preserved under switching. Okay, so now we're going to look into what this implies for the design of the switching logic. So we discussed that the switching should not be too fast. And so dwell time is one property that allows us to capture this. If I start with the family of monitoring signals that I originally defined yesterday, and I introduce a design parameter called dwell time, which is just a positive number, tau d, what I'm going to consider is the following switching logic. I'm going to, instead of always switching to the index of the monitoring signal that's the smallest, I'm going to wait tau d units of time before carrying out the minimization procedure and picking the smallest index. So at each tau d units of time, I'm going to find the index p bar that corresponds to the smallest monitoring signal. I'm going to check if that monitoring signal is smaller than the one I'm currently using, and if yes, I'm going to redefine my value of the switching signal to be p bar. Otherwise, I wait another tau d time units and repeat. Okay, so this is maybe the simplest switching logic that you will find. Okay, so my switching signal is no longer just the argmin of the monitoring signals, but it's the sampled version, sampled by the dwell time. And there are basic results that are known, as I already mentioned, in stability of switch systems, which say that stability, or in this case detectability, which are closely related, is preserved if you choose the dwell time to be large enough. Okay, so this may suggest that such a switching logic is quite suitable, but in fact it's quite difficult to obtain a bound on the estimation error E sub sigma in terms of ET star, because you lose performance if you choose the dwell time large enough. For stability, there will be long periods of time when you're not using the index that you should be using, and so the performance is degraded, which is reflected in possibly not being able to satisfy this other property that we want from the switching logic. And in fact, for nonlinear systems, this may not be suitable at all, because bad things can happen while you wait. For example, the state of the system can escape to infinity, or in practice it will not, but it will become quite large. So in general, the way that you may think why dwell time switching logic is not very suitable is because in practice, I would say that imposing a hard bound on the inner switching intervals is not a good idea, because if something unexpected happens, so if the performance goes below the bar that you want to enforce, before the dwell time has elapsed, you have no mechanism to correct that. So this dwell time switching logic is, so to speak, too inflexible for practical purposes in many cases. So for this reason, one also uses a different idea, which is to slow down the switching not by means of a fixed dwell time, but by means of hysteresis. So I'm quite sure that in some form you all have seen this idea. So let me describe what it means in the present context. So we start with a family of monitoring signals, and we impose a hysteresis constant. So we choose a constant h bigger than 0. What I'm going to do is I'm going to initialize sigma and then look at the index of the smallest monitoring signal. But again, rather than immediately switching to it, I'm going to switch to the smallest index only if the difference between the smallest monitoring signal and the monitoring signal I'm currently using exceeds h. So h, the hysteresis constant, will be my threshold of tolerance. I'm going to tolerate the difference up to h, but if the difference becomes too large, I'm going to switch to the monitoring signal that's currently the smallest. So that's a fairly standard hysteresis idea. If the smallest one is smaller than mu sub sigma by at least h, or if you want a version of this where the factor is multiplicative rather than additive, so this is called sometimes scale-independent hysteresis. This has some advantages because if I scale all the signals mu, then this relation will not be effective. So either way, if you want to do additive or multiplicative hysteresis, if this condition is satisfied, I'm going to reset sigma. If it's not satisfied, I'm going to keep monitoring until this condition is satisfied. Okay? So essentially, from the simplest switching logic, we start with the ideal formula that we would like to mimic but don't want to implement, which is the sigma of t is always the argmin of the monitoring signal. And then you want to introduce some sort of sampling, either in time, which is the dwell time switching logic, or in space, which is that you tolerate some mismatch between the monitoring signals. You don't always use the smallest one, but only up to some additive or multiplicative tolerance threshold. And this latter idea is what the hysteresis switching logic is doing. Okay? So what is interesting about the hysteresis switching logic is even though it does not explicitly slow down the switching the way that the dwell time does, some properties of hysteresis switching logic can be shown that are quite nice, that translate into slow switching. Okay, so you do the hysteresis based on the spatial variation of the monitoring signals, but then you draw conclusions about the time behavior of the switching. And this is where the technical meat of the analysis is, where the hysteresis switching logics are concerned. So the first type of result that is known is the following, that if your family of plants, or if the range where the unknown parameter lives, which is the script t, is finite, if the monitoring signals are all monotonically increasing and one of them is bounded, then the switching stops in finite time, which is quite an interesting result. It takes about one paragraph to prove it. You can find the proof in chapter 6 of my book. It's not very difficult to prove, but this is quite nice because switching stopping in finite time means you don't have to worry about stability, or in this case, detectability. It's automatically preserved. Some comments on this. So finite uncertainty range is certainly restrictive. So that means if you actually have an infinite range, then you have to absorb the gap into a model dynamics and do some further analysis. So this is a somewhat idealized situation. One of the monitoring signals, mu p star being bounded, is typically guaranteed by the multi-estimator. If EP star goes to 0 exponentially fast, and then you take something like L2 norm, then this property will be enforced. Another thing, and this relates to the question that you were asking me yesterday, here this result requires that the monitoring signal, each monitoring signal mu p, be monotonically increasing. So if you take the monitoring signals to be L2 norm of the estimation errors, this is verified. But if you were, for example, to use estimation errors themselves, which dance up and down in an arbitrary fashion, then this result wouldn't be applicable. So it does require certain care in defining monitoring signals. But one thing that saves us is that because of the scale independence property that we have with multiplicative hysteresis, the monitoring signals need not all be monotonic until possibly after some scaling is applied to all of them. Okay, so there is some leeway here, but certain assumptions need to be enforced before this result can be applied. Now, this applies, as I said, to the somewhat...
Question?
Yes, go ahead.
Dan, this is Peter. Peter, thank you for sending the slides yesterday.
Sure.
Question is, how do you know mu p star is bounded?
How do I know if mu p star is bounded?
True.
So, one example of this, let me go back and actually remind all of us about one example that we looked at yesterday. So here was an example where I have a plant without the disturbance, and I build the multi-estimators in a specific way that's basically enforcing some damping here so that the estimation error, EP star, goes to 0 exponentially fast. And then the second building block here would be that I need to define my monitoring signals. Let me see where that is. To be, for example, S here, that mu p dot is EP squared, or mu p are just the L2 norms of the estimation error. So this is one example where I can get this property, because if I integrate the square of an exponentially converging signal, I would get something that's bounded forward in time. Okay. If I implement the second, go ahead.
How do you, what do you mean by P is bounded? P star is bounded. Yeah,
how do I enforce that P is finite? I couldn't hear you all that well.
What do you mean by P is finite?
Yeah, well, it's an assumption. So like I said, if P is not finite, then the result does not apply off the shelf. But what you can do is reparameterize your problem in terms of finite P and absorb the rest of the uncertainty that you actually have into model dynamics. So let's say that your uncertainty is an interval, so it's a continuum. Let's say I'm going to sample it into 10 or 100 points, and then reparameterize my problem in terms of this finitely many points, and the rest is going to hopefully be handled by the inherent robustness of my controller design. So P comes from the original parameterization, and then sometimes I can transform a continuum of uncertainty into a finite set, but of course I have to worry about the gaps that I leave behind. If that's not feasible, if you don't want to do that, then the result I just mentioned is not relevant, but I'm going to mention some other results that may be more relevant.
Thank you.
So, like I said, this result applies in the idealized scenario when there are no disturbances on model dynamics, because only then can I hope that EP star will converge exponentially fast. I need to make sure that my monitoring signals are appropriately defined to ensure their monotonicity. And like we just discussed, finiteness of the modeling uncertainty is another constraint. So this is sort of a starting point, but it's not, practically speaking, it's usually not enough. You can go much further in this direction. Let me show you one thing that I think is particularly interesting. So this basic result was obtained by Hispania and Morris in the late 90s. And they showed the following. They showed that if I go through the design I described for the case of linear plants, still with no unmodeled dynamics, but with bounded noise, okay, if I have bounded noise, then typically I will not have a bounded mu p star, and so the previous result does not hold, and in fact you can see that the switching will continue forever. But interestingly, they showed that you can prove the existence of average dwell time. So this is a relaxation of dwell time in the average sense. So you have switching that may occasionally violate the dwell time constraint, but you asymptotically or in the average sense have a dwell time, and this can be formalized, and they did this. And this average dwell time actually has a pretty direct dependence on the hysteresis constant. And intuitively, as you can guess, probably if I increase the hysteresis constant, that means I'm becoming less fussy or more sloppy in my switching logic, then the average dwell time will grow. So the switching will become slower and slower. And this also, the second component that I need to have is a bound on E sigma in terms of each individual estimation error EP. And in this context, it can also be obtained. There is a formula like this. The details are not so important right now, but the important thing here is that the gain, so to speak, from the L2 norm of EP to the L2 norm of E sigma depends on the size of your uncertainty set. So this is still for finite uncertainty set, and also on the size of your hysteresis constant. Okay. And then we have further results that sound from your questions like you would be interested in looking at them. I don't have them here on the slides, but if in case of continuum uncertainty, by modifying the switching logic in the way that I alluded to a minute ago, you can obtain similar results, and I'll be happy to give you specific references to those and discuss them further. So this
basically tells me our last inequality tells that I should probably have the smallest number of supervisory controllers because it's proportional to the number of uncertain parameters, the number of discretizations in the P, right? So does it?
Right. So you can
tell me that if I synthesize, I should synthesize with the smallest number of controllers, or?
As a first approximation, here you can think of having one candidate controller for each possible value of the parameter, and in that case, the cardinality of the uncertainty set and the cardinality of the controller family would be the same. But when we go to continuum uncertainty sets in the plan, we can still work with finitely many candidate controllers, so the two would be different. And in that case, this factor in the gain would actually be the cardinality of the controller family, like you say. So this will be finite. But you need to modify the switching logic to adopt for a continuum in the uncertainty set. Does it make sense?
Right.
Okay, so just one more thing that I wanted to mention. As you can see, I'm at the end of my slides and be happy to open up for discussion. I know you guys have several problems that you may be interested in solving that are sort of more application relevant than the toy example that we've looked at, but I just wanted to highlight one thing. So I personally have not done very much with practical applications of supervisory control, although we do have a few results that we looked at. And my co-authors, in particular Joao Espana, have also done some application-related studies based on supervisory control. One example, sort of a toy example that we've looked at quite a while ago, one of the earlier ones that we used to show the efficacy of the supervisory control framework, was parking a unicycle type non-holonomic vehicle with uncertain parameters, P1 and P2, which you can think as arising from unknown or miscalibrated size of the wheels and the distance between the wheels. And what was interesting about this example, I'm not going to show you details of this, but we have a paper that details the approach and also some simulations, which are not very surprising, but just the vehicle does, the controller does work. So you want to park this car at a specified configuration, let's say at the origin facing certain way. And we know that even if all the parameters were completely known, this problem cannot be solved by continuous feedback. And one type of control solution that is commonly employed for the case of known parameters is a switching control. So you basically have a set of some undesirable configurations from which you have to make a logical decision to move away from them, and then you switch on a continuous feedback that's defined everywhere away from those configurations. So the interesting feature of this example is that the candidate controllers themselves are switched or hybrid controllers. Each of the controllers that I'm using, T1, T2, and so on, has switching in it. This is a low-level switching. And then you have higher-level switching orchestrated by the supervisor, and this is how this problem is solved by the supervisory control framework. So the thing that I usually emphasize in relation to such problems is that if you're going to have switching anyway at the higher level by means of the supervisor, this is quite suitable for working with quite general controller mechanism at the lower level, for example, switching or some other type of time variation for low-level controllers. So in this sense, this framework is quite flexible in allowing more general candidate controllers than, for example, is typically used in traditional adaptive control. So with this, I'm done with my presentation, and I'll be happy to provide you references and aspects that are interesting to you, and we'll be happy to try to answer more questions and continue discussing things with you in the future as well.
Thanks a lot.
Any questions?
So I have a question about the possibility of having the supervisory controller control reference commands to the controller rather than control switching itself. Is there any literature on that? And the reason is, from an applications perspective, you might want, for example, for a chiller, you might want to reduce the speed or the torque on the chiller output rather than change the whole controller on its own. So would that something that would fall under the supervisory control topic or no?
Right. So I would say maybe two things in response to Ali's question. One is that, yes, there are some papers that have been written, but not very many. There is one, my former student, Lin Wu, with whom you might have even intersected at Illinois. He wrote a paper on supervisory control of time varying plans, which was an extension of what I discussed, because I discussed the plan that's fixed, unknown but fixed. But we also looked at time variation, and there, just to illustrate that the control design still works, we had an example of tracking a reference trajectory. I think there's also work by Dan Miller in Canada, Waterloo. They also looked, I believe, at reference tracking, but there isn't very much. So I think that the theoretical challenge is not very big there, because if I am able to reduce the problem to stabilization of the aerodynamics, I think I can pretty much use the tools that I described. So maybe the most constructive way, I would say, is to look at some specific tracking problems, and rather than looking at some general results that might have been published, which may not exist in fact, I would just try to use the same methodology, but sort of adapt it from scratch to the problem of interest, which is a tracking problem. I believe there will not be a lot of difficulty in generalizing from stabilization to tracking.
Any more questions? Sure.
So this is Shalabh Gupta. I just have this question because we are addressing this proposal issue. So we are dealing with very large scale systems, not very small systems where things are interconnected, a lot of components, and they are talking to each other. So is there any literature that you can suggest which is dealing with these kind of systems for supervised control?
I didn't understand the last sentence. Is there any literature that...
Is there any literature for the discrete event supervisory control, or just supervisory control of these systems?
So you probably know the old work by Wanham and Ramage, which looked at discrete events, and they also actually used the term supervisory control that somehow is kind of confused with the way we use supervisory control. So you might find some useful ideas there. This is, I can dig out the references and send them to you, but this is back to the 1980s. We have not looked at discrete events. It may be that somebody more recently looked at it. I would have to check. But off the top of my head, no. We looked at continuous time plans and sort of the controllers that we work with are not necessarily continuous controllers, but they run in continuous time, and the state spaces are Euclidean spaces in most of the work that I'm aware of.
Those papers are, I think, 1987 or something.
I think one of them is a book that you can download for free.
Yeah.
So,
It's pretty old.
no, it's a 2009 or 2005.
No, the papers.
No, the book has got a book that you can download.
What's the last name?
WONHAM. He's at the University of Toronto.
So other question
Yeah, I just wanted to get his opinion though. Have they ever been useful, the kind of thing that Joanam and Ramaj are doing?
The kind of thing that...
Are they practical at all?
I'm sorry, the clarity of the sound is not very good when several of you are speaking. So.
Do you think they're useful? The stuff that Joanam and Ramaj, that models, right? That kind of approach.
Mm-hmm.
Have they been applied in anything real or just theoretical exercise?
Right. So like I mentioned, we have one paper that I can send you, which we wrote a few years ago to compare the advantages of supervisory control with traditional adaptive control with Espana and Morris, and we looked at a few, I would say, toy application-related examples. One was this unicycle parking that I mentioned. There are also some other mechanical systems that my co-authors looked at that I have to recall what they were. So I would say that there's been some work on looking at examples, but not maybe a systematic effort to do transition to application by our group.
I have other question. This is regarding, I think there was a question yesterday about the discrete event supervisory control rather than continuous supervisory control. So can you shed some light, comparing between these two approaches?
So comparing the supervisory control I described?
Yes, versus the event.
Sorry, can you repeat?
So can you give us some highlights on how to go from continuous domain to discrete domain for constructing a discrete event supervisor and vice versa?
So by discrete domain, you mean not discrete time, but actually discrete sets in which signals or states take value.
Right, exactly.
Correct. So yeah, off the top of my head, I cannot say very much, for the following reason, that the basic building block for our design is to have a control solution for each possible value of the parameters. So you would have to start by telling me if you still are interested in switching because of some adaptation properties that you want, then you would have to start by giving me a family of candidate controllers, and in discrete event case, you would have to decide what control methodology you're using. And like I said, there are these discrete event controllers by Ramage and Wonham, and there's an active area now. My former colleague Chris Hachikostis works on discrete event control. There's also a group in Michigan that works on them. I'm not an expert. So once you give me the candidate controllers, then I would say that I could try to adopt similar ideas to orchestrate switching between them. But because I'm not too familiar with the low-level control solution, it's not easy for me to say what will carry through and what difficulties I'll encounter. I have not looked at that.
We were thinking of more like the low level could be still continuous time controllers or continuous state controllers, but at the high level we have the discrete event controller, supervisor. Does it make sense? More like a hybrid.
So you're saying your individual controller is a continuous time, and your plant is also continuous time?
Right.
Right. So then you're basically focusing on the switching logic would be your discrete event. So then I don't see a lot of difference between, I think, what you have in mind and what I described. I think this would be falling then into the same category, because if the individual controllers are continuous, the plant is continuous, and you have a switching logic, which is a discrete event system, because my my switching signal takes values usually in a discrete set. So there could be some additional insight from discrete event literature that we could use. We haven't done that. But I think what I described is basically using a discrete event system on top of the continuous controller. So I think it would be quite the same thing.
So what is the number of your cardinality of sigma is huge? What do you do? That is M, the number of controllers at the end.
Right. So I think one idea that could be useful is so there's two ideas I think that could be useful. One is to forget many of them at the modeling stage and absorb them into robustness margins that you're trying to show in the end that you will have, right? So if I have a huge number of controllers, possibly because I have a very large set of possible plans, maybe that's not a very good starting point for my methods, right? So I would then maybe try to focus. Remember, I had at the beginning this example where I had a union of two disjoint intervals, and I said, well, we can just use two controllers. I would try to somehow simplify the parameterization first. I'm not sure what exactly is huge, but if, let's say, you have 1,000, I could try to maybe pick 20 that provide good enough coverage, and then work from that. And then we have results that will tell us what kind of robustness margin I will have, and then you cross your fingers and hope, and you would have to validate that a posteriori, that the things that you left in the gap are still going to be covered. The other idea that might be relevant to this idea of state sharing, so if you really have a nicely parameterized family where the range of uncertainty is large, but the way that it enters is mathematically nice, maybe linear or polynomial or something like that, then you can actually try to work with it using state sharing in the way that I described. So you would have to strike a balance between maybe getting a nicer parameterization and working with a large but somehow nicely parameterized controllers within the method I described.
Thank you.
So another question is regarding dwell time. So among the problems of hysteresis is that you might have to switch back and forth very frequently without really having control over that process. If you decide to go with dwell time, so you have kind of a systematic weight that you have, how would you integrate that into the design of your supervisor? Because I couldn't see, when I looked at the slides, I couldn't see really where you would integrate that. And the other thing is there any literature available on adaptive dwell time, depending on which states you're moving from, of system states you're moving from or to?
Right. So there's things in the literature that's quite rich, and then there are things we personally looked at which are a bit more limited. My personal view, I don't like dwell time. I like hysteresis. And this may not be relevant to the kinds of problems you may be interested in, but in my own work, I found dwell time initially looks very promising and very appealing because it's quite simple, and it explicitly bounds the switching in time, right? So it explicitly tells you something about the switching being slow enough by design. But then when you do the analysis, you have other things to worry about, like the bounded gain that you have from the non-switch to switch estimation errors. So there are technical details that become very, very messy, even for linear systems. And the other thing that I don't like about dwell time for nonlinear systems, I think that any sort of practically minded solution would suffer from the same problem, is that this lack of flexibility in taking corrective action in between the points, right, the endpoints of the dwell time interval. So for that reason, I personally found hysteresis to be maybe better from the point of view of analysis going through, right? And so but of course the challenge then is to show that hysteresis, even though it doesn't directly impose dwell time or anything of that kind, it indirectly can be shown to lead to similar properties. So that's sort of the direction that we've been looking at. Now, there are some other people, so there is I've seen, I would have to look and remember, but I've seen some results by Claudius Ipersis, who's now in Groningen and who was working with Steve Morris on this topic a few years back, and he was looking at adaptive dwell time, where indeed you would have a dwell time that varies with dependent on where you are in the state space. And they have some results that we could look at and see. But personally, my work, I've been leaning more towards hysteresis because otherwise the analysis becomes much more difficult. Now, for practical implementation, I think that this is quite open-ended. You could try whatever works and see. In simulation it might work very well, but I would be more limited in showing rigorously that the system is stabilized if you're using dwell time, especially for nonlinear dynamics.
The way that he's doing is better. Because if the system is not changing too fast, it will automatically adapt to your dwell time, right? Because you're basing it on the relative change in the VP or absolute change. So the hysteresis, I think, is a better implementation idea.
Right. So you see what will happen is initially there could be very fast switching because you have to remember about the initialization of these monitoring signals. So you may have one signal that's converging to zero and another that's not, but initially they are such that they're close together. And so you may initially have very fast switching if you use hysteresis, if you do not impose dwell time in a hard way. But in the asymptotic or in the average sense, you can show that these effects will be transient and will eventually disappear. I'm not sure if that answers your question.
Yeah, maybe you could have some hybrid thing so that there's a minimum dwell time that you can cause.
Right.
And the hysteresis to this.
Yeah, my main when it comes to, because I've been trying to implement this on a motor drive, and in a practical application, if you we haven't tried hysteresis, but we've been trying dwell time, and it works well, but then the selection process of the dwell time, there's no systematic way that we're finding right now. Maybe I've been looking at the wrong literature, because this is all practical literature rather than the rigorous proofs or so. But for hysteresis, one thing that I could see as a problem in implementation is unless your estimator outputs and your errors are are bounded and are very clearly bounded and kind of can be clearly identified from each other, then your hysteresis might go nuts. And I don't know, maybe I'll have to implement that and see, I guess.
Not if you use the scale thing, because scale thing is independent of what the values are, right? So if you do mu p times 1 plus h thing,
right?
Yeah,
then you have to design for the percentage that you're using.
Right.
I think it's definitely true. It's definitely true that the things you will see by implementing dwell time would look nicer than the things you will see by implementing hysteresis, simply because dwell time just dictates certain regularity in the switching, and for hysteresis, you would need to show that, right? It's not a priori guarantee. On the other hand, if you're after rigorous analysis of the whole thing, then tables will eventually be turned. So things will look nice for dwell time, and that may be good enough, for your interest. But I may have less confidence in doing stability analysis with it. With hysteresis, under appropriate conditions, I might be able to compensate by showing that if I choose the hysteresis constant correctly, then actually every dwell time will follow. And what that means is that maybe the hysteresis will go nuts for a while, but it'll eventually settle. So I definitely agree with you that with dwell time, you will never see any kind of irregularities that you might see with hysteresis. But whether that can always lead to stabilization is a more difficult question to answer.
Yes, right.
Any more questions? No, I have a quick couple of questions. On your slide number 30, the architecture that is showed, there was EP signal which was going on. So you're comparing a plant output to your estimator output. I was wondering if that idea is similar to the prediction error idea in adaptive control?
You're talking about this signal here?
Yeah.
Right. So this is, I think it's the same as what people have used in adaptive control. It's indeed the output prediction error. So it's not, you know both of these signals, right? You know Y and you know YQ. So sometimes people call it estimation error, which is a bit misleading because you're not estimating anything. It's indeed exactly the output prediction error. So you expect the error to go to 0. If it does, then it predicts or suggests that the index is correct. If it doesn't, then it falsifies the corresponding model and says that that cannot be the true plan. So yeah, this idea is, I would say, is quite standard.
The other question I have, probably it goes back to maybe Shalab's question, that the architecture that you have shown is for handling parametric uncertainty in the plant. I was wondering if you can extend this to, so for example, if you design controllers based on a different objective, for example, you want to try to track different reference trajectories rather than take care of different parametric uncertainties in the plant.
So the situation I have in mind is I have a plan that's known, and I have maybe some kind of gain scheduling objective where I need to track one signal, and then after a while I need to track another. And I start with a bank of controllers, one for each objective I'm going to track, and then I switch according to the schedule that I'm given. I switch between them to track the changing reference, right? So I would say that may be in some sense an easier problem to handle because for the plan that's known, I'd be able to do the analysis much more easily. We haven't looked explicitly at this, but I would off the top of my head, my guess is that some of the analysis that I presented would not even be necessary. I'd be able to come up with a switching logic that conforms to the schedule and then do stability analysis using some, but not all of the tools that I mentioned. That should be fine. Whether somebody has looked into that, I would have to see, but it reminds me of, more standard gain scheduling problems, but the fact that you're tracking reference trajectory makes it not quite standard. I'm not sure if that exact problem has been studied or not.
Okay, well, my question was more on, even if you have the parametric uncertainty in the plant, plus if you want to do some sort of gain scheduling. So,
I guess you can apply the same thing to even disturbances too, right?
Right, yeah.
It should work, I think. This whole multi-estimator type of idea, you can assume different disturbance, for example, weather conditions in a building.
Right, yeah.
So you can have different estimators and then see, what is the actual condition, one of the parameters, and then switch your logic that way.
So I think the question here is that how many conditions you have, how many trajectories you want to follow. For example, for aerospace application, it could be tons of different.
That is, I think, Achilles heel of this approach is how many estimators do you need? How do you design so that you've got a minimum number of controllers and estimators and still accomplish the goals of the control? I think that is a key research issue. And how do you know that?
The good thing is that we haven't looked at that, which means there are some new things ahead of us that we could investigate. I definitely don't have an answer, but it sounds like some of these ideas could be useful, but we would have to see.
You haven't really explored the properties of individual controllers. If individual controllers are optimization-based, output control, anything you have to watch out, anything you can make use of? So can you comment on that?
Well, for the candidate controllers, the requirements were somewhat high level, right? So they need to provide detectability. Other than that, you're free to use whatever control you want. So I think that maybe for some classes of controllers showing this detectability may be harder. For some other ones that I have in mind, it may be easier. So we tend to use sort of specific controllers with a view towards showing detectability. But as long as you're able to show the detectability property, as far as I can think, it doesn't matter what type of control you use. So this result is sufficiently high level that it can accommodate your favorite controller as long as you can somehow fit it into the framework we have for showing detectability.
The thing is, could you have designed your controllers so that you use the minimal set, that M is the minimized, while achieving the overall response of the system under all potential uncertainties?
Right. Right.
Actually, that may be one way of reducing the number of estimators and number of potential controllers that you need.
Right. That question is open as far as I know. Any kind of questions having to do with using the smallest number of controllers that do the job, of course, this has to be related to what uncertainty set you have. I'm not aware of very much that has been shown for this. So not a lot of optimality-based designs are available. Usually what I've seen is you start with some parameterization, start with some number of controllers that is taken as having come from whoever handed us the problem, and then we do the analysis. But we haven't done much with trying to go back and see what is the minimal number of controllers that we can work with. And that would be quite interesting and useful.
MPC guys, they also claim that they can do supervisory control, right, by switching among different MPC controllers, model predictive control.
Yeah, we haven't specifically looked at an MPC. Again, I would think that the sort of the level of abstraction we've been working on is equally tolerant to any of your favorite controllers, but we do need the detectability property. And by the way, the detectability is not new, right? So if you look at the papers by Steve Morris on adaptive control from early 1980s, I think he called it tunability or something like that, but it was essentially detectability is known to be key for traditional adaptive control. So we're not saying anything new in that regard. And whatever control you use, again, you would need to show that, or if you cannot, then the analysis would need to be changed, because without detectability property, I don't know how to do the analysis. But with it, I don't care what your favorite controller you give me, which I think is sort of a good thing about the flexibility of the design.
And also for yourself or other people, based on your approach, so what are the practical applications have you done or your colleagues have done?
So the question is what practical applications we've looked at?
Yeah, so either you or your colleagues based on your approach.
Right. Like I said, not much. We've looked at some toy examples of, I think we looked at the inverted pendulum. I think my co-author, Hispania, looked at some other system that I'm forgetting, but also was a toy, maybe MEMS example. And then we looked at the control of non-harmonic systems, like the unicycle parking. So in fact, I would have to find the information, because I think that Steve Morris also had a master's student that looked at some specific application, but it was a long time ago. I forget what it was. So personally, I have not looked at much, but I should be able to find a few examples that use specifically the approach I discussed, that sort of comes from the same research group, although not done specifically by me, so it's not at my fingertips right now. And then there's probably more applications that use this general idea, but perhaps not the exact setting that I described. So if you want, I could follow up with you by email and sort of give you some of the reference that I'm aware of, and we might be able to even find something that I'm not aware of that's out there.
What would be the foreseeable difficulties when someone tries to apply your method to practical applications?
Well, obviously, it would be verifying the assumptions, right? So I have the assumptions about the multi-estimator. So you need to design the multi-estimator. So if you give me a practical system, that would be a challenge to see if it falls into any of the known classes for which we have multi-estimators satisfying the properties we want, or if it doesn't, then maybe designing it from scratch. Then for candidate controllers, you have to, typically, you would have to give me the controllers that work one for each value of the parameter, but since I insisted on the detectability, which may not be something that you would have, enforced before you listened to my presentation, so there may be some mismatch there. We need to work on that. The switching logic, I think, would be fairly independent of what problem you're solving. So it would be mostly verifying the needed properties for the multi-estimator and the needed properties for the candidate controllers so that we can plug them into the approach I described.
Then would you say that your approach is more like a design by construction? Because you are constructing a supervisory controller that guarantees stability and whatever performance metrics?
That's exactly correct. Right, exactly correct. So the way that we wrote down these properties was so that the analysis is almost automatic. So it's sort of correct by design. Right, and so, but of course the work is hidden into verifying these assumptions for the particular case. And if you start with the particular case you have in mind and the assumptions are not quite satisfied, we might to some extent be able to go back and fiddle with the analysis to fit into your framework. But it's hard to predict, whether that will go through. So yes, our design is correct by design, so to speak. And it's modular because we require different things from different blocks that are not interconnected. So it's modular design that's correct sort of by construction. But of course, then in practice, the challenge is to make sure that the various blocks work as we require them to.
I can see in your case, right, some higher level algorithm that groups your parameter space into, cluster it into, say, K groups, right? The K is a parameter that I need to select by optimization. Now I go and design my controller, say, use MPC or something like that, right? And then see what its performance is, and then pick the one that is gets you some criteria, satisfied. And the nice thing about it is that now, since it's a supervisory control, is pretty straightforward in this case, and it's correct by construction. All you're doing is, while designing, you're basically designing it the correct way, I would think. Okay.
Right. And another thing,
all the selection criteria to select what that K should be, some sort of MDL or big type criteria.
Right. Right. And I would just add that even if we cannot give a complete proof because maybe some assumptions are not satisfied, in our experience, actually, in practice, it would work quite well. So in that limited number of application-related scenarios that we've looked at, sometimes, or typically, I think the practical, the simulation results or the empirical observations are ahead of the theory, in the sense that the theory is quite challenging unless the assumptions are exactly satisfied. I may not have a complete proof of stability, but still, typically, I would see that it works quite well.
In the state and control signals. Has anybody worked on that?
I'm sorry, could you repeat, please?
What if I had constraints on my planned states and controller signals? Like my actuator should have some saturation effects, and my state should be in certain regions, that kind of thing. So you have constraints on your states and control variables.
So in the framework that we have, I think that these would have to be absorbed into the disturbances that our model accounts for. And so you would need to show me that you have some bounds on these effects. So if you translate them into some error signals, disturbance signals in the system, and you give me some bound, I can work with that. And I would be able to describe how this propagates through to the end result. So if you are solving a tracking problem and you have some actuation effects or some other errors that are bounded by a small number, then I would be able to describe to you how that translates into a small offset in the resulting tracking. If you...
I do see that maybe you could use some of the MPC guys type of things by putting in the state constraint, control constraints, and designing your controllers, and then use some sort of things from machine learning type of thing to decide on the number of potential controllers, right? So that will be the outer loop optimization for your synthesis. And work with this framework. This is you're combining two different domains, you know, the Murari type approach versus this one.
Right. Yeah, we haven't gone in this direction. It's definitely an interesting thing to look at. What we've done is more like a gridding approach, where we would calculate the coverage that the grid that we take provides for the space, and then we would use the gain analysis to see if the resulting robustness margin is enough to cover all the gaps that I left. So, and that way you could move towards describing the optimal number of points on your grid that you need, but it doesn't quite give you a handle of where to put the points, because this is like a worst case approach that we looked at. So there's definitely room for using some learning theory or machine learning or other types of things for refining this the gridding approach. We haven't gone that way.
If the drop time is very long, would it be possible, especially the system is non-linear, when you do the switching, would it be possible to get into a non-stable mode and the system become unstable?
I didn't quite understand the end of your question. So you said if the system is nonlinear, go ahead.
Yeah, if the drop time is very long.
No, but his steady system will take care of that, right?
I'm not sure. Are you assuming away the difficulties, or if drop time is very long, could anything happen during your switching? And
so personally, I would not use dwell time. I would not use large dwell time for a nonlinear system unless I'm sure that its solutions are somehow well behaved, that I have some compact steps which they will not lose, because otherwise my transient behavior will get worse as my dwell time is increased. But I do want to increase my dwell time, because if it's too small, then switching will destabilize me. So I will be at a situation where I cannot resolve the conflict. So personally, for general nonlinear systems that are perhaps not very nicely behaved, I would probably use hysteresis or some combination of hysteresis and dwell time for this reason, that things can happen to the nonlinear plant while I wait, and I don't have a handle on that.
Time varying systems. Time varying systems?
So for time varying systems, there is one paper that I mentioned with my former student Lin Wu. The basic, so if one line summary is that if the plant changes but slowly enough, so that the time scale at which the plant varies in time is slower than what my supervisor is doing, the switching of my supervisor, then things still carry through. So the analysis becomes more challenging, but under certain assumptions, the analysis can be done, and sort of empirically, I think it still works if you use it on specific examples. So you have to make sure that if your plant is too fast and gets away from your supervisor because the scale at which it changes is too fast or comparable or faster than the supervisor switching, then I think this approach will break down. So you can very slowly time-varying plants you can handle. Reasonably fast time-varying plants, probably not in general.
I think anything that changes too fast, you should probably take care of it in the controller.
Okay.
And so supervised things should only be for slower things, you know. So if it is very too fast, you design your controller wrong.
It can change fast if it doesn't go very far, right? So by fast, I mean something maybe not as restrictive as the way it sounded. So if it goes fast far away, then I'm in trouble. if it changes fast but within a small neighborhood in my plant parameter set, or if it goes far away but very slowly, then I'm in this.
Quality conditions, like, so you need to have designed your controllers for those things beforehand, or how does it work? Suppose I start having faults in my plant, right? Or in the sensors. What do I do?
Yeah. Typically, I would take the controllers as given a priori. So, for example, for this mechanical example, this unicycle parking, the controllers were switch controllers, so that made this more interesting, but they also were off the shelf. So I think that if you want to give me specific controllers, I would have to look on the case-by-case basis how they fit.
So you would have considered that as part of your...
Yeah, so for example, like if you have like a stiffness of a beam, and it's a parameter stiffness, it changes, it's like a parameter.
You're assuming to be gradual changes. What if it is a sudden change?
It's still a parameter change.
Yeah, with the delta, right? Delta P. So, I guess is very example at things shifting, right? Okay. So maybe it can still be handled then. Okay. I think there is a proposal that you guys can do by merging this ideas with maybe the MPC type thing for the controller design. And your research questions is what is the minimal set of controllers and estimators that you need to switch them on. One nice thing about this is that as long as your detectability and your error is going to go to zero with this one, right? So, correct by design.
First thing we should do is maybe type MPC and Supervisory into Google and see if somebody has already looked at MPC controllers, because we have them.
Okay. All right. Great, thanks.
Okay, let's thank.
Thank you.
Yeah.